Hello engineers, welcome back to another video. In this video, we are going to discuss motion planning for robots using a very popular sampling-based path planning algorithm called RRT, Rapidly Exploring Random Trees. Along with RRT, we are also going to discuss some other sampling algorithms as well, like the probabilistic roadmap algorithm and an improvement of the RRT algorithm called the RRT Star algorithm. We are going to run our RRT algorithm on the Spot robot. Spot is a quadruped robot that is developed by the company Boston Dynamics. Let's have a quick look at the simulation that we are going to use. This is the gazebo simulation of our quadruped Spot robot. Here we can see the Spot is present. The robot is present in a construction-based environment where we can see the different obstacles over here. And we are going to visualize our path planning algorithms in this environment. And this is the RVS visualization of the same simulation environment that we saw before. Here we can again see our Spot robot that is present in the same environment. The robot is visualized on the cost map of the given environment. Due to the gazebo simulation being resource heavy on my local computer, we are only going to visualize these path planning algorithms on this RVS application. Here we will see the robot plan its path and will also see the robot following that path. First, let us simulate the PRM or the probabilistic roadmap algorithm. Now let us try the simulation of the RRT algorithm. In the PRM algorithm, our first step was to sample the different points in the environment, and then an optimal path over those points was constructed. However, in the RRT algorithm, our sampling of the points and the construction of the path were being done simultaneously. Let us now discuss the technical details of the RRT algorithm and the PRM algorithm along with RRT star to understand this behavior and the differences between them. Motion planning is the computation problem of finding a sequence of states or configurations that take a robot from the start state to a goal state. For a 2D based path planning problem, we are usually given the start state and the goal state along with a cost map. The cost map describes the free spaces and the obstacles that are present in the environment. Usually, ground-based robots solve their path planning problems in 2D using these cost maps. Other robots like drones or robot manipulators need to solve this path planning problem in 3D. If we extend this path planning problem to higher dimensions, excluding use cases in robotics like protein folding or design-based problems, then we have to solve this path planning problem in n dimensions. For 2D based path planning problems, intensive computations and search techniques are useful. They are computationally efficient and usually give us the optimal path or the shortest path required. However, as we increase the dimensions, these intensive search methods are usually not feasible. Even when extended to 3D, these search methods like A star are usually not preferred. To quickly find the solution to these path planning problems, we have a set of path planning algorithms called sampling based algorithms. Sampling based algorithms do not directly use these intensive search methods that we apply on graphs. Rather, they work on the principle of probability. Consider this example that we have been given over here. We have the start state and the goal state. Along with that, we have certain obstacles that are present in this map, C1 and C2. As the first step, we randomly sample points in this environment, as we can see these black dots over here. Then in the next step, we join these randomly sampled points to get a graph structure, as we can see over here. Then on this graph structure, we apply any shortest path algorithm to derive a path that takes us from the start to the goal. These first three steps that we took in this sampling algorithm are called the construction steps. This fourth part over here constitutes the query part of the sampling algorithm. All the different sampling algorithms differ in the way how they sample the next point and how they prepare this graph structure. Due to the random nature of these algorithms, these are quite fast. However, they may compromise on the optimality of the final solution. Because of their speed, these algorithms are usually preferred for path planning in high dimensional spaces. One very popular sampling algorithm is RRT. RRT stands for Rapidly Exploring Random Trees. Consider the ith iteration of the RRT algorithm, where we have already constructed a graph that we can see in black over here, and we have sampled a new blue point that we can see over here. Now the next step of this algorithm is to decide which point of the original graph is going to connect with this new sampled blue point. We join this randomly sampled blue point to the nearest neighbor point of the original graph. As we can see, these are the distances of the nearest nodes, and the node with the minimum distance is selected to form the edge. This nearest neighbor query can be efficiently solved using spatial computing data structure like KD trees. Spatial computing data structures deserve a video of their own. In brief, spatial data structures store these 2D points in such a way so that these points can be efficiently retrieved and these queries like nearest neighbor can be solved quickly. In order to make the RRT algorithm more efficient, these new points are sampled in a biased way. These points are sampled to be biased from more free space area. This bias towards free space ensures more exploration. There are some other implementation details as well. First, if the newly sampled point is too far away from the current graph, then we linearly interpolate that point closer to the graph and select that point as the newly sampled point. Second, during random sampling, we have a probability to always sample the goal node. This detail ensures that our RRT algorithm will eventually end up at the goal node. There are certain extensions of the vanilla RRT algorithm to make them more suitable for certain kind of problems. Now let's discuss the structure of the search for some of these sampling algorithms. The first one we have is the probabilistic roadmap. Probabilistic roadmap is a relatively simple algorithm where we sample the points in the space and form a more or less complete graph, as we can see over here in the blue. Then we apply a shortest path planning algorithm like A star to get the path that goes from start to the goal. The structure of search in the RRT algorithm forms a tree, as we can see over here. Once the complete tree has been constructed, then we can again apply any shortest path algorithm to get the path from start to the goal. RRT star is an extension to the RRT algorithm. It provides two additions. First, we do not connect the randomly sampled point to the nearest neighbor node. Instead, we connect it to the node that minimizes its distance from the start to this newly sampled point. This is something similar to what we do in a traditional grid search algorithms like the Dijkstra algorithm. Second, once we have connected this newly sampled point to the current graph, we apply a rewiring function. We iterate over the neighbors of this newly sampled point and check their distance from the start node that passes through this newly sampled point. If the distance is less, then we rewire a new path from this newly sampled node and remove the previous edge. These two modifications help the simple RRT algorithm to give better optimal paths. These modifications result in a rather straight form of tree compared to the vanilla RRT algorithm, as we can see over here. Alright, so this is it that we had to discuss for the RRT algorithm. Now let us have a brief look at the code. All the code that we are going to discuss is already uploaded on GitHub, and the link to that would be present in the description box below. First, let us discuss the RRT algorithm. Here is the RRT function that computes the RRT path. We pass in the start index and the goal index along with the cost map. As a first step, we initialize the index list. This is the index list that we are going to sample our points from. Next, we set up the expand distance. This is the same threshold that we discussed when we have a point that is sampled too far away from the current graph and we want to bring it closer to the current graph. Then we have a loop that iterates for some number of iterations. For each iteration, we select our next random node from the index list that we derived above. The getRandomNode function over here samples us a point from the index list. Here is the first implementation detail that we discussed. There is a slight probability of the goal node to be sampled in this random sampling as well. The goal sample rate for our visualization was set to be 20. This means that the goal node has a 20% chance of being sampled. It has been set to such a high number to run the simulation faster. And then we calculate the nearest neighbor of that newly sampled point. This function getNearestNodeIndex gets the nearest neighbor for us. Due to the small scale of our RRT algorithm, we are not going to use the complex data structures like KD trees. Here we are instead calculating the Euclidean distance for each node that is present in our graph and assigning it as the nearest neighbor. This implementation is a bit time consuming. However, due to the small scale, we can easily do this. After choosing the nearest index, we interpolate that nearest index to the newly sampled point. The interpolate function over here does that work for us. In the interpolate function, the first step is to set the threshold that we discussed. Then we use the trigonometric functions sine and cosine to interpolate between the nearest neighbor and the newly sampled point. Collision checking is done after we have interpolated our new point. In this part of the code, we set the color visualizations that we were seeing on the RViz window. After our iterations are complete and we have found a path that takes us from the start to the goal, we calculate the detailed grid-wise points that forms a path to take us from the start to the goal. Finally, this computed path is returned to the robot to follow it. Now let's discuss the PRM or the probabilistic roadmap algorithm. It takes the same parameters, start index, goal index, and the cost map. Here as well, we have the similar step where we initialize the nodes which we are going to sample from. After initializing the nodes, we sample the points from this index list. Then we generate a graph from these sampled points. In the generate graph function, we are using the data structure KD trees. For each point, we sample some of its nearest neighbors and connect that point with these neighbors. Doing this connection exercise for each of the points, we get a graph. Since for each iteration, we need to compute many different nearest neighbors, hence it is beneficial to use KD trees over here. After generating the graph, we run the Dijkstra algorithm on this graph. Dijkstra returns us a set of points from those sampled points that the robot can follow to reach the goal. In order to give a detailed path for the robot to follow, we call the interpolate function on each of the successive points. The interpolate function over here is quite similar to what we had in the RRT algorithm. Using trigonometric functions, it does a linear interpolation. On applying this interpolation, we get a detailed grid-wise path for the robot to follow. We send this path to the robot and the robot follows it to go from start to the goal node. All right, so this is all that we had to discuss in this video. If you like the video, press the like button and subscribe to the channel for more such videos. And thank you for watching. Bye.